July 16th, 1945. The first atomic bomb. In today's video, we're simulating the Trinity test bomb, frame by frame. Hi, I'm Justin, and this is Slowed. Let's begin with a single plutonium-239 nucleus in red. In our simulation, we can fire a neutron at it. When they collide, the nucleus absorbs the neutron, becomes unstable, and splits into smaller particles, releasing energy and additional neutrons. This is fission. We'll represent each reaction product with distinct colors, and a legend will help us track them. But not all collisions cause fission. Sometimes the neutron scatters away harmlessly, or even misses outright. We'll model 4 different nuclear events: elastic and inelastic scattering, absorption, and fission. We'll also add the click of a Geiger counter for each fission event. Now, let's scale it up. Simulating 30 plutonium nuclei, we can observe the chain reaction. If there aren't enough atoms packed closely together, the reaction fizzles out. This is called subcritical. Here, 3 fission reactions occurred, several scatters, but 27 plutonium nuclei remain. We had incomplete fission. We need a way to increase the reaction. Let's introduce a neutron reflector, also known as a tamper, made of uranium-238. Notice how it bounces stray neutrons back into the core. Now, nearly all of the plutonium undergoes fission. The reaction sustains itself, reaching criticality. This time, we've added 100 plutonium particles. The entire reaction happens faster, even though there's more plutonium. That's the basis of a nuclear chain reaction. More nuclei to react, more neutrons, and the faster the reaction. So, we can reach supercriticality by adding more nuclear material. Let's try 1,000 plutonium atoms. A new problem arises. Notice the neutrons can't easily reach the far side of the core until they collide, scatter, or fuse with the plutonium in the way. What if we released the initial neutron from the center? To achieve an explosion, we need supercriticality, where the reaction rapidly escalates. That was 50% faster. The core is supercritical. Now let's put it together. We'll use 2,000 green particles to represent the 111 kilograms of uranium-238. This will be our tamper, reflecting neutrons and containing the core during fission. Then we'll use 500 red particles to represent the 6.46 kilograms of plutonium-239, ready to undergo fission. But how do we release the neutrons from the center at just the right moment? We can't simply put an electric device inside the core. Any wires leading out would create a weak point, allowing the core to blow out the side, so to speak. And we can't place a constantly emitting neutron source in the center. It would cause premature fission, also known as a criticality event. This actually happened twice in Los Alamos, tragically killing 2 scientists. Both accidents involved the same plutonium core, which was later nicknamed the Demon Core. Exactly how the Trinity test gadget released neutrons from the center at precisely the right time is still partly classified, but by looking at the original documents that were leaked to the Soviet Union, and by deduction, we have a pretty good idea. Let's start with 2 different nuclei: polonium-210 in yellow and beryllium in green. Over time, the polonium decays by releasing an alpha particle, shown in blue, which strikes the beryllium, causing it to split into carbon and a free neutron, It's an elegant solution to generate neutrons without electronics. The problem? It would emit neutrons continuously if we placed it together all the time. So, we'll place a thin metal foil between both materials to absorb the alpha particles. That way, when polonium releases its alpha particles, they're stopped by the foil and never reach the beryllium. Here's our neutron initiator. 100 yellow polonium nuclei, 100 green beryllium nuclei, and a thin gold foil in between, blocking alpha particles until it's crushed. Only when the core is compressed does the foil rupture, letting the beryllium and polonium mix. With the initiator in place, our core is ready for the final compression sequence. Remember how I said earlier we can boost the total energy by adding more plutonium? Well, there's another way. We can also do this by compressing the nuclear material so that those plutonium nuclei are closer together. By cramming 1,000 particles into a fraction of its original size, we'll increase the core's density to supercriticality. And at the same time, the crush will rip the gold foil, allowing polonium and beryllium to mix and release the neutrons from the center, thereby setting off our nuclear chain reaction. Let's build the compression mechanism using conventional explosives. We'll start with a single copper wire. Copper is chosen for its high conductivity and low resistance, ensuring minimal energy loss. As we fire the switch, the generated electric field travels down the wire, moving at nearly half the speed of light. In our simulation, we can visualize this as a pulse of electrons racing toward the detonator. Now, let's introduce a second wire of a different length. Notice how the pulses arrive at different times. Bad news if you need perfectly synchronized explosions. Let's expand to 32 wires, placing them spherically around the outer skin of our bomb. We see that a single firing switch causes the detonators to fire out of sync. The shockwave would arrive at our plutonium core at different times and cause a catastrophic effect known as asymmetrical implosion. This happens when one side of the compression is slower than the other. Instead of a perfect inward squeeze, the plutonium is deformed. Pressure squeezes out the thin side, punching a jet of molten metal and plasma through the gap, and the core never reaches full supercritical density. In short, a mistimed detonator turns a precise nuclear collapse into a lopsided, dirty blast. To fix this, we'll introduce precision delay circuits, historically known as the X unit. These small modules calculate and adjust each wire's firing sequence so that every detonator receives its pulse at precisely the same moment. Timing is everything. Now let's focus on the detonators, the red dots at the end of each wire. Each detonator is an exploding bridge wire detonator, or EBW for short. A thin copper bridge wire sits in a small block of explosive. Will represent different molecules in situ, randomly scattered inside for the explosive material. When an electric pulse arrives, the bridge wire vaporizes, which initiates an explosive chain reaction. In our simulation, you can see the shockwave start near the bridge wire and move outward in all directions. However, for the implosion to work correctly, we need a directional shockwave, one that channels its energy inward rather than outward. To achieve this, we can surround the EBW with material that will help to reflect those shockwaves. And if we increase the purity of our explosive material, we get a stronger, more directional shockwave to help compress our core. Notice, if we place 4 EBWs evenly around the core, we have an asymmetrical shockwave. It's lumpy. This is because our EBW detonators produce diverging shockwaves, a convex wave. While powerful, this shockwave will not uniformly compress our plutonium core. We need a concave shockwave, an imploding wave. What if we shaped our explosive into a trapezoid? Notice the wave narrows at the end, but still remains lumpy, still convex. What we need is a lens. We'll build our lens using two explosives. Composition B, our fast explosive, which detonates at 8,000 meters per second, and barytol, our slow explosive, which fires at roughly 5,000 meters per second. Watch what happens if we chain the explosive types together. The shockwave begins in composition B and propagates to the left. The center of the shockwave slams into barytol first, decelerates, while the edges, still in composition B, keep racing ahead. The result? The shock front warps into a shallow bowl. In our first attempt, we can see the barrier between the two explosives was calculated incorrectly, and results in the shockwave reaching focus before it hits the core. Now we've added a second region of composition B, shown in green, to re-accelerate the shock front. Notice this design gives us two boundaries to shape. As the shock front arrives at the first boundary and enters the pink barytol, the center slows, while the trailing edges continue on at 8 kilometers per second. Inside barytol, the front is warped into a flat shockwave, but when that wave hits the second boundary, the edges accelerate first, with the center lagging behind. The once flat front folds inward, forming a bowl. This concave wave will collapse precisely at the plutonium surface, compressing the core from all sides. Once the lens design is perfected, we scale up. Let's put it all together. One firing switch, 64 wires with precision timing, 16 X units, 32 EBW detonators, explosive lenses, 129 kilograms of aluminum, 111 kilograms of uranium-238, 6.46 kilograms of plutonium-239, 500 grams of beryllium, and a few grams of polonium-210. Now, let's run the simulation. The countdown begins.
5, 4, 3, 2, 1.
The firing switch snaps. At once, all 32 bridge wires flash to vapor. The explosives ignite. Shockwaves race inward and plunge into the explosive lenses, where their speed is slowed to just over 5 kilometers per second. The wavefront is now shaped into an implosion wave, a perfect collapsing circle. The ring of detonation enters the last layer of composition B explosive and is accelerated toward the core, faster now and focused. The shockwave slams into the aluminum pusher at over 8,000 meters per second, or 18,000 miles per hour. The aluminum vaporizes, then ionizes into a fourth state of matter, plasma. Next, it compresses the uranium tamper, which holds out briefly before also succumbing to the immense pressure. Finally, the force converges on the plutonium core from every side, crushing the nuclear material down to 1/3 its original size. Here, we'll slow down even further. At the moment the core becomes supercritical, each 10 seconds of our video equals just 1 nanosecond in the simulation. The gold foil ruptures. Alpha particles from polonium hit beryllium, and the neutrons they release flood the supercritical core. Fission escalates until hydrodynamic expansion tears the core apart. a flash of radiation forms as the fission products suddenly escape. Let's zoom out to a 20-mile view. The shockwave reflects off the ground, kicking up dust, while the plasma fireball rises, creating an updraft that sucks in desert sand and radioactive particles, mixing them. All of that happens in less than 1 second. But here, in Slode, we live inside every frame. Want to see the full code to run your own Trinity test? Become a patron and gain access to behind-the-scenes footage and the code used in the simulation, all on the Slode Patreon page. Like and subscribe for more Slode reality. Thanks for watching.